will be on something a little different than the previous one, something on graph theory and specifically domination subdivision. So, because not everyone is familiar with graph theory necessarily, I'll start with some introduction and some terms we'll use. Then we'll move on to a characterization and end with an algorithm, and as we progress it will become clear what the talk is about. So we have to start at the beginning. What is a graph, or a simple graph? Just a set of vertices V, which we graphically represent as dots, and a set of edges of unordered pairs of vertices, which we represent as lines between two vertices. So we say those two vertices are adjacent, there's an edge between them. So a graph has a simple graphical representation. This is an example of a graph. A set of vertices, 2, 4, 6 in this case, and a set of edges between some of the vertices. So that's what we mean by a graph. You'll notice here that these edges form what we call a cycle. So there's a cycle in this graph. If a graph does not have a cycle, for example, if I remove those two edges, then there's no cycle in this graph. Then we call the graph a tree. So a tree, T for tree, is an acyclic graph and also connected, meaning that I can get from any vertex to any other vertex by traversing some edges. So it's one piece. So acyclic, there's no cycle. So there is a unique way to get from one vertex to another vertex. For example, these two, the left one and the right one, I can only get from one to the other using those two edges, traversing these two edges. So that's acyclic and also connected, just one piece. So we'll call that a tree. So we're mainly concerned with graphs that are trees. What is a rooted tree? Well, if I go one step back and I label this vertex as vertex B, if I want to refer to the tree T rooted at the vertex B, well, essentially, I just put the vertex B at the top level and draw it essentially with all edges going down from V. So V had two adjacent vertices, those two are the next level, and then from them there are two adjacent vertices for this one and another one for that one. So the edges are directed down from one level to the next level essentially. So this is the rooted tree T rooted at V, and V can be any vertex in the tree, and I denote it by T sub V. Okay. So it's not too complicated, pretty intuitive concept. So what is domination, first of all? A subset of vertices, D, is a dominating set if any vertex not in the set is adjacent to some vertex in the set. So if I just look at this example, which is also a tree, then I need to find a set of vertices, ones I've indicated here, for example, such that any vertex not a dark vertex has to be adjacent to a dark vertex. Then the set of dark vertices, that is a dominating set. So, for example, this vertex dominates itself and anything adjacent to it. And we're interested in the minimum number or the minimum cardinality of such a dominating set, and we call that the domination number of the graph. So in this case, it's easy to see that one vertex cannot dominate the whole graph. There's just no way you can do it. But these two do dominate the whole graph. So the minimum number, the domination number, is 2 in this case. Okay. So that's the idea of domination. What is domination subdivision? Well, the domination subdivision number is E sub gamma of a graph. The minimum number of edges I have to subdivide in order to increase the domination number. So what do I mean by subdivide? If I have the same example, when I subdivide an edge, for example this edge, I replace it with a vertex adjacent to those two vertices. So if I want to subdivide this edge, for example, then it gets replaced with a vertex, and I join that vertex to these two vertices that were adjacent originally. So this graph I obtained, or this tree I obtained, I obtained by subdividing this edge, for example. Okay? So that's the idea of subdivision. So when I look at the domination subdivision number, I'm looking at what is the minimum number of edges that I need to subdivide. So I add a vertex essentially, so that I increase the domination number. Might not be 1, in this case it is. I can subdivide any edge I want. For example, this one, if I subdivide this one, I get this tree. And now it's not difficult to see that two vertices, no matter which ones I pick, cannot dominate this. Yes?
Are these numbers defined only for trees?
No, we're specifically looking at trees,
Okay.
so I make my example a tree. It's defined for any graph. I'm just looking at a tree because the talk is specifically focused on trees.
Okay.
Just to keep things simple. Trees are pretty nice to work with. So in this case, when I subdivide this edge, I need 3 vertices to dominate this graph. 2 just can't do it anymore. So by just subdividing one edge, I've increased the domination number from 2 to 3. So the domination subdivision number of this tree is 1, because I just needed to subdivide one edge. I can't necessarily pick any edge, but if there is one edge, and I subdivide it, and I cannot dominate with the same number of vertices, I increase the domination number, then the domination subdivision number of this graph is 1. So those two ideas, domination and domination subdivision, are important for this talk.
So can you sometimes subdivide and not increase?
I think this one has one. If I subdivide this edge, it's difficult to see without actually drawing it right. If I subdivide this edge, so I put a vertex there, then these two vertices, these dark vertices still dominate the graph. Because this one will be adjacent to this one, so these 3, if you imagine one there, will be taken care of, and these 2 still. But if I can find an edge, so that I increase the domination number, then it's 1. If I need 2 edges for, suppose, a bigger graph, then the domination subdivision number will be 2, and so on. So, I forget when exactly, the level for trees specifically shows that the domination subdivision number is always between 1 and 3. So, at most, we need to subdivide 3 edges to increase the domination number. So, we can classify trees as class 1, 2, or 3, depending on what their domination subdivision number is. Haynes, with some co-authors, characterized trees where the domination subdivision number is 3. So, you know what those trees look like? So, onto a characterization, specifically when the domination subdivision number of a tree is exactly 1. Karami and some co-authors characterized these trees for which the domination subdivision number is 1, as in our example. But it was in terms of sets that weren't characterized or are not characterized, and it doesn't seem that those sets are very useful. So, though it's a characterization, we can't really do anything with it. So we thought about this for a while, and it turns out that one can characterize these trees with domination subdivision number 1 in a much more useful characterization. Just using the set that I'll call N of a tree, That's the set of vertices not contained in any minimum dominating set.